Yeah, hello everyone. Welcome back. So in the previous lecture, we discussed the introduction to the process dynamics and control. So we understand what is the process is and why dynamics important and why control is required in real industries. In today's lecture, we will continue from there and explain the core concept slowly using the my notes. Okay, please follow carefully and I will explain everything step by step. Okay, now let us understand what is a process again. Okay, so a process is a conversion of raw material into useful product. Okay, here here for example, a reactant A and a reactant B is combined to form a product C. Okay, so this conversion happens under specific temperature and pressure. So process is a input and a transformation and get a output. Okay, now let's see what is the dynamics. So dynamic means how the process change with the time. Okay, if the temperature, pressure and concentration change with the time, the process dynamics. So in reality, most of industrial problems, most of the industrial processes are dynamics. Okay. So the main objective of chemical engineering is conversion of raw material into valuable products. Okay, this conversion must be safe, must be safe and then efficient and economical. Okay, so now let me discuss about the applications. So where the process dynamics and control are applied. Okay, so in the aerospace and rocket system, control is required to maintain the stability and directions. Okay, a small mistake can lead to a failure. So that's what very important in process dynamics and control, their applications. Okay, in many systems we must maintain the liquid level and overhead the pressure. So this is possible only with the process control. Now let's see one more example, that is in petroleum and petrochemical industries. So here temperature, pressure and flow. So these must be tightly controlled. So without control, plant operation is impossible. Okay. Now we'll discuss one more example is nuclear reaction. In the nuclear reaction, in the nuclear reactors, control is extremely important for safety. Okay, even small deviation can cause dangerous. A small deviation can be very dangerous. Like even one more application is hazardous chemicals. For hazardous chemicals, control is required to protect human life and the environment. Human life and the environment. So whenever safety, quality and efficiency is important, the process control become very essential. Okay. So now let us go to the next one. Understand an important idea using the simple example. Okay, in process dynamic, we have mainly talk about two a process. One is the steady state process, and another one is the dynamic process. So a steady state process is a process in which variable do not change with the time. Okay, for example, if you take temperature, pressure and flow remain constant with the time. So the process is at a steady state. As a steady state, the process is calm and balanced. When I come to the dynamic process, is a process which variables change with the time. Okay, if the temperature, level, and concentration varies with the time, and the process is called dynamic. Okay, most of the real industrial processes are dynamic. So in the real plants, we disturbance always occurs. Okay, uh, why means when the fluid flow may change, temperature may change. Okay, and reaction rate may be changed. Okay, because of these disturbances, the process never stay steady for long time. So this is what need for control. So the question is here, how do you handle these changes? So we use control system to bring our process back to the our desired conditions. So here control is required mainly because of process are dynamic. This is why understanding the process dynamics process dynamics is the foundation of a process control. So next we will understand this concept using the practical the practical reactor example. So now imagine you are the engineer you are the engineer and responsible for this reactor. Okay, yeah, responsible for this reactor. Okay, so this is a stirred tank reactor. Okay, a chemical reaction is taking place. So if the temperature is not controlled, the reaction become unsafe. Okay, so here your goal is very simple. So maintain the reactor temperature at the desired value T equal to Tr. Okay, so let's see what are the inlet and what are the outlets are there. Here the water inlet is Ta, this is called inlet temperature, and W is the water flow rate, and here Q is the heat supply rate. So then we need to get the final products are T and W. Okay, so this is the value is decided based on safety and product quality. That is what this is the T value. Okay, so now see the different case studies in the mixed reactor. Then the just now what we discussed, our aim is to maintain the T equal to Tr. Okay, so now let's see the first case study. Suppose the reactor becomes faster. That means more heat is radiated inside the reactor. Okay, the reactor temperature starts increasing. Okay, then what will happen if you do nothing? The temperature may go out of a control. This is called lead to runaway reaction. Suppose if temperature is more, this become a runaway reaction. Okay, so we reduce a heat input or increase a cooling. So this is how control prevents the accidents. This is how control prevent the accidents. So now see the second case study. Okay, so the feed temperature drops, suppose. So the reactor temperature starts decreasing, right? So that means what if temperature becomes too low? If temperature becomes too low, the reaction rate decreases. Okay, then definite effect on the product quality. It's effect on the product quality. Okay, then what is the third case? Third case is this is the best case. That means temperature exactly equal to our Tr. That means T equal to Tr. So everything is working perfectly. In this case, the controller does nothing. So control action is required only when there is an error. That means there is a difference between T minus Tr. When the error is there, then only the control should take action. Suppose if you go to real plants, if you go to any real plants, if you go to any rail plants. Okay, so there we should always focus on the temperature, pressure, and flow, and maybe composition change together. Okay, can a human operator react instantly? Can any human operator reactor instantly? No, right? So that's why automatic control are used. Okay, that's why we use automatic process controller. Okay, process control is not about only the equations. Most of things like that. Okay, not about equations. It is about mainly. It's about mainly safety. Okay, then quality, and the main important thing is reliability. Okay, so now the question is, how would we mathematically analyze such dynamic systems for dynamic system? So for that purpose, we are going to use the Laplace transforms. We are going to use the Laplace transforms. So till now we understand the process. So we understand the process and why control is required. And this is what you understand till now. So now comes to an important question. How do we mathematically describe the behavior of a dynamic process? How we mathematically describe the behavior of dynamic process? The answer is using the differential equations. Okay. So dynamic processes are described by these differential equations. But solving differential equations directly is very difficult. Directly, it's very difficult. So especially in exams and real problems. So this is the where Laplace transform comes into the picture. Okay, Laplace transform is a mathematical tool that simplify our work. Okay, so it converts difficult differential equation into simple algebraic equations. Okay, so this is what converts mainly differential equations into simple algebraic equations. Okay, in time domain, variables are depending on time t. Depending on time t, in Laplace domain, it converts them into S domain. Okay, now let's see Laplace of t equal to f of s. That means time domain to, this is time domain to S domain. So in S domain, analysis become very easy. So Laplace transforms convert a function of time into function of s. If f of t time function, Laplace transform is f of s. Okay. So you do not need to worry about the integral form now, but I hope you know about in BTech first year. Laplace f of t equal to integral 0 to t e power minus st into f of t into dt. So Laplace transform help us to study system dynamics, and it help us to find system response also. So it help us to design control. So this is why Laplace transform is the backbone of a process control. This is the backbone of process control. Okay, so Laplace transform is not just mathematics; it's tools that helps engineers to understand and control our real process. This is what real process. So now, what you understand what Laplace transform is, let us see the basic forms. So now let us clearly understand the properties of Laplace transforms. Okay. So these properties tell us how and when Laplace transform can be applied. So now discuss about the first property. Okay, here t less than 0, that means f of t equal to 0. So when t greater than or equal to 0, f of t is exist. So the first property is about the time. So in the Laplace transform, we assume the function start at time equal to at time 0. Okay, for all time before 0, the function value is 0 only. Okay, suppose in the physical meaning, what exactly it means, the physical process cannot respond before the input is applied. So take simple example, uh, heat a water. Okay, so you cannot heat water before switching on the heater. That's why Laplace transform is called unilaterally transform. Okay, so now let's see the second property. The second property explains what Laplace transform actually does. Okay, this Laplace transform converts function of time into function of s. That's what f of t tends to f of s. This change from time domain to s domain makes analysis easy. Okay, so far we learned two important ideas, these two. Okay, first the function start at time 0. Second, time domain function converted into s domain functions. Okay, now let us apply these property to simple and commonly used functions. Okay, okay, what are those things? Now let's see. So first one is a step function. A step function represents a sudden change. Okay, sudden change. Okay, so for time less than 0, the function value is 0. For time greater than 0 or equal to 0, the function value becomes a. Okay, so the step input represents switching on something. So suppose if you go switching on heater or maybe sudden valve opening, applying to constant voltage. These are some of the examples how this step input you understand. Okay, suppose let's see the Laplace transform of a sub magnitude A is divided by S. That's what A. This is what Laplace transform is equal to A by S. Okay, because we can take the value when there is a with respect to time change. Okay, so now let's apply this A by S, e power minus A into e power minus S. This is what Laplace of A, right? Laplace of T to Laplace of A. That's the change in the magnitude of A. So when you keep it here, e power minus S to f of t dt, we know the Laplace of f of t. So there f of t, keep it A. So then apply the integral for this e power minus s into a, then this is what minus of e power minus s by minus s 0 to infinity. So when you apply this one, then you will get 1 by s. Okay, that's called Laplace is equal to a by s. Okay, so this result is used very frequent in control systems. So a step input is a time domain becomes 1 over as in a Laplace domain. Okay, so when keep it equal to 1, that's called unit step function. So when the mention unit step input means you should always remember 1 by s. Okay, this is called unit step function. Okay, so now we understand the step input. We will see the ramp input and then impulse, exponential and sine inputs. All are these extensions are the same idea only. Okay, so this is what Laplace transform help us to represent real physical inputs in a mathematical form. In a mathematical form. So now next two important inputs used in the Laplace is ramp input. Then we'll discuss about the impulse input later. Okay, understand these will make control systems very easy. Okay, now ramp input. A ramp input represents a signals that increasing gradually with the time. If you see this graph, it's increasingly gradually with respect to time. Okay, at time 0, the value is 0. At time increases, the value increases linearly. Okay, so step like what discussed, step input is a sudden, ramp input is a gradual. So this is the main difference, step and ramp input. So ramp input represents the slow and continuous changes. Okay, like some of the example, if you want to know, examples are gradually increasing temperature, or maybe slowly opening the wall. Okay, then gradually decreases or maybe increases flow rate. Okay, so this is what this ramp input used to test tracking ability of a control system. Okay, now we see that with respect to Laplace transform, Laplace of t into u of t equal to integration of 0 to e power minus s2. This is what your input, right? This is what your ramp input, keep it t. So now using the apply Laplace transform of Laplace of uv, okay, then uv dash minus, this formula and the mathematical representation, that t into, this is the form. Then we have integration 0 to infinity 1 into, so this is the complete term e power minus s t into dt into dt. So then apply this Laplace transform, then finally we will get, substitute all the things, and then you will get 1 by s squared. When you keep f of t equal to t, then when you do the Laplace transform t into u of t, then you will get 1 by s squared. So this is ramp input, help us to study how well a system follows changing the inputs. So this is importance of ramp input. Now we will see one more one more input, that's called impulse input. I think I didn't mention here. So the one more important is impulse input. The third important is impulse input. Okay, this impulse input represents a very sudden input applied for a very short time. Very short time we apply this. Okay, so that means the magnitude is very large, the duration is extremely small. This is the main difference. Here the magnitude is very large, the duration extremely small. So impulse is mainly a mathematical concept, but it is not applied physically, but it's very useful for the analysis. This is the advantage of impulse. Okay, impulse is like a hitting a system with a hammer, the normal example. So the force acts as very short time. That's what we discussed previously, right? So Laplace of for impulse, Laplace of delta t equal to 1. So impulse response tell us as the fundamental behavior of a system. So this is what impulse input reveals, the inherent dynamics of a system. Inherent dynamics of system represent the Laplace of delta of t equal to 1. So now, so those three are very important. The one is step, then we have a ramp, then impulse. So the step input is changes a sudden and constant, and ramp input is gradual and increasing, and impulse input is sudden and very short. This is the main difference between these three. Okay, these three inputs from the foundation of a control system analysis. Okay, if you understand this step and impulse and ramp clearly, the control systems become very easy. Okay, so now we'll study the exponential function and sine inputs, which appear naturally in a real process. Okay, so an exponential input represents a signal that change very fast at the beginning and slowly later. Right? At time 0, the value is maximum. As time increases, the value gradually decreases. So you can able to see here from here, this graph. Okay, exponential means fast, the fast change first, slow change later. Okay, so if you know about the some of the real examples, cooling of cooling of a hot liquid. The simplest example, like discharging of a tank or decay of concentration in a reactor. So this is why exponential term appear frequently in a process dynamics. Okay. So the Laplace transform of Laplace transform of e power minus a t equal to 1 by s plus a. So Laplace of e power a t equal to 1 by s minus a. Like when you substitute of Laplace of f of t, then when you substitute this one, then you will get finally 1 by s plus a. Laplace of e power a t equal to 1 by s minus a. So here the parameter a, this is the parameter a, decide how fast the signal decays. Okay, exponential input models naturally growth and decay in the process. Okay, then we discuss about the sine input. F of t equal to sine of omega t or maybe sine kt. Okay, or sine omega t. So a sine input represents oscillatory behavior. Okay, so this is the signal continuously goes up and down. If you see the signals, it goes always up and down. This is sine signals. Okay, the behavior repeats with the time. So sine means, definitely sine means oscillation. So the normal example, that means AC electrical signals and the vibrations in mechanical systems, then oscillations in control loops. So whenever see oscillations, then definitely sine and cosines are involved. So the Laplace transform of sine omega t or maybe sine kt is equal to k by s square plus k square or maybe omega square. So here k and omega or maybe omega represents the frequency of oscillation. Okay, sine input helps us to study the oscillations and frequency behavior of a system. So the same way cos and sine is kt and cos is kt. So please remember all these formulas, or maybe you can derive it by using the Laplace transform formula. So now till what we discuss about the step and then ramp, then impulse, then exponential input, then sine input. So step input represents the sudden change, and this is what gradually change, and impulse input is sharp, and then exponential is decay or growth, and then sine input represents the oscillations. So understanding these inputs is the foundation of analyzing the dynamic system using our Laplace transform. Okay, so next we'll see the Laplace transform of derivatives. So then these are used to analyze the system behavior. So now we are coming very important property of Laplace transform. The property is called Laplace transform of derivatives. So this is extremely useful in process dynamics and control. So let's see how to get the Laplace transform derivative property. Okay, so we already know the definition of Laplace transform. Laplace of f of t equal to integration of 0 to infinity e power minus st into f of t into dt equal to f of s. Okay, now we want to find the Laplace transform of a derivative of a function. Okay, so let's know about integration of 0 to infinity e power minus st into f of t, that is df by dt into dt. Now we apply the integration by parts. Apply the integration by parts. So that means integration of u into du equal to uv minus integration of v into du. So apply this formula here. This apply formula is apply this first term formula and second term formula. Then just substitute the limits 0 to infinity. So then you will get so 0 minus f of 0 plus s into f of s. Okay, so here we represent this is as a f of s because we know this is what we taken as a f of s. We substitute here f of s. So now we find Laplace of dy by dt is equal to s into f of s minus f dash of 0. Okay, this is what we got the final results for the Laplace of dy by dt. So the Laplace transform of the first derivative becomes s times f of s minus the initial value. So that means notice that initial condition appears automatically. Okay, so this is why Laplace transform is very powerful. It converts derivative into algebraic terms. Okay, initial conditions are handled naturally. Okay, so this is what we discuss starting onwards. Differential equation becomes a algebraic equations. Okay, the same like a Laplace of second derivative. Okay, for the second derivative we got s square into f of s. But now two initial conditions appear here. One is initial value, other one is initial slope. Okay. Higher the order of derivatives, more initial conditions will appear. Okay. Then we have Laplace of third derivative, that is mean dq of f by dt cube. For third derivative, we got s cube into f of s and three initial conditions. So each derivative adds one initial conditions. So okay. So remember always for first derivative, one initial conditions. For second derivative, two initial conditions. For third derivative, three initial conditions. Order of the derivative equal number of initial conditions. Okay. So in process control, system models are differential equation. Then Laplace transform convert them into algebraic equations. This is the make analysis and control design very easily. So this is the foundation of a transfer function development. Now we will see the simple example to find the x of t. So find the Laplace transform of x of t for the difference equation, that means dx by dt plus x equal to 1, x of 0 is equal to 0. So they provide the initial conditions. Now we know Laplace transform f of t is converted into f of s. Now apply the Laplace transform for the equation. That means Laplace of dx by dt equal to apply Laplace to this one, apply Laplace to this one, and Laplace of 1. Okay. Then we know the formula of dx by dt. What is dx by dt formula? S into f of s minus f of 0. So substitute here s into x of s minus x of 0, and then x of t become x of s, then 1 become a 1 by s. So here what they provide initial condition, x of 0 equal to 0. Sometimes they provide some of the values, or maybe 1, 2, or 8, different values. Then we should substitute here. Okay, it's become 0 means 0. So that means x of s make common, s plus 1 equal to 1 by s. Then get a final x of s is equal to 1 by s into s plus 1. Okay, this is what till now we found x of s. Okay, not x of t. So we need to find x of t. Okay, till now please remember only till x of s. So then we'll go to the inverse Laplace, then only we can get the again time domain. Again we need to change some frequent domain to time domain. We'll explain that concept later. So but right now please try to find out for all differential equation x of s. When you find x of s properly, then only we can go for the inverse Laplace. Okay, the same way can you do for the two different examples, that is second order differential equations, and they provide the initial conditions also. Now can you solve this one? Can you please find out what is the x of s? This one as well as these equations. Okay. So till now we learned how to convert time domain function into Laplace domain. Okay, now we will learn reverse process. We learn the reverse process. Okay, this is called inverse Laplace transforms. Okay, that means f of s became converted into again f of t. Inverse Laplace transform converts s domain to back to the time domain. So this is the steps. This is the step necessary to obtain the actual time response of a system. So we need actual time response of a system. So why we need this inverse Laplace? So we analyze the systems in a S domain because it is easy, but real physical behavior exists in the time domain. Okay. So in practice, we did not use mathematical definition. We use the standard Laplace transform tables. So just go through the textbooks. So then we'll got to know all the formulas. Laplace transform of f of s equal to f of t. Okay. So the simplest method using the standard Laplace transform. If you know about all the formulas very easily. Okay, so let's see what they provide you in the example, the previous example, dx by dt plus x equal to 1, x of 0 equal to, this is what they provided. So from here, find the Laplace transform, then calculate the inverse Laplace transform. So we already derived what is the Laplace transform of x of s. So what is the x of s we got for previous problem, the same problem, but here we just take for the x of s, we need to find this x of t. So till here find x of s. So now let's come to here. So here we know x of s is equal to 1 by s into s plus 1. Now we apply the partial fractions. So for this x of s value 1 by s into s plus 1, then divide into partial fraction, just find out a and b values. So if you know a, just substitute here 1 by s into minus 1 by s plus 1. Then apply the inverse Laplace. Okay, and again from s domain to time domain we need to find out. Then Laplace inverse of x of s is equal to Laplace inverse of 1 by s, Laplace inverse of 1 by s plus 1. We know 1 by s is equal to 1, 1 by s plus 1 is equal to e power minus t. So we know very well Laplace of 1 equal to 1 by s, Laplace inverse of 1 by s is equal to again 1. Same like e power minus is 1 by s plus 5. So Laplace inverse of 1 by s plus 1 is equal to e power minus t. Just substitute here, then we'll get the final answer for x of t. So finally we got in the time domain format. Okay. So till now we learned how to take Laplace transform, and now I will show some powerful shortcuts. So this shortcut help us to understand how system start and how it ends, and how delay and accumulate work. Okay. Now let's go by one. The first one is final value theorem. This is what limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s. Imagine you start a process and wait for a long time. Wait for a long time. After long time, the system settles. Okay. So final value theorem tells us the final steady state value directly. Okay. No inverse Laplace needed. So suppose just check what happens when s goes to 0. Okay. This gives the your final value. Suppose if you go to the real-time example, final liquid in a tank, or maybe the final temperature of a reactor. So the final value theorem answers where the system finally stop. This theorem mainly works for the stable systems. Okay. So now we will explain the initial value. But before that, I want to show you the proof of final value theorem. This is the final value theorem proof. So we know limit t tends to infinity f of t equal to limit s tends to infinity s into f of s. So here, what is the proof? So now see 0 to infinity df by dt e power minus dt is equal to s into f of s minus f of 0. This is what we know for the derivative of df by dt. That's what we discussed previously, how we got this final answers. The final output in the S domain. Okay, now apply limit on both the sides. Okay, that's what limit s tends to 0, integration of 0 to infinity df by dt e power minus s t into dt equal to limit s tends to 0 s into f of s minus f of 0. This is what we apply both side limits. Okay, now see here, now substitute s equal to 0 here, then we'll get 1. Okay, that's what 0 to infinity df by dt into dt equal to the same thing we just write here, limit s tends to 0 s into f of s minus f of 0. Okay, now this is what your f of t. This is, we know very well df by dt is equal to f of t. So now apply the limits to each limits. That means limits f of t, limit f of t, t tends to infinity. Okay, minus f of 0, minus your f of 0 equal to limit s tends to 0 s into f of s minus f of 0. Now compare these terms. Okay, now this is the term will cancel, f of 0 will cancel. So then what is the final term? Limit t tends to infinity f of t equal to limit s tends to 0 s into f of s. So this is what your final value theorem. Finally we achieve by applying the limits on both the sides for the df by dt. Okay, this is what till now we discuss. Now let's go for the initial value theorem. This is limit t tends to 0. This is the main, here t tends to infinity, here limit t tends to 0, because we are going to do initial value theorem. Limit t tends to 0 f of t equal to limit s tends to infinity s into f of s. Now think about the very first moment after applying the input. So initial value theorem gives the starting value of the response. So here largest means very fast behavior. So checking as s tends to infinity gives the initial value. This is the concept behind that one. So checking s tends to infinity gives the initial value, because large s means very fast behavior. Okay. So real-time example means if you want to know about initial temperature change. Okay, what is initial temperature change? And then initial speed of response. Okay, so initial value theorem answers how does the system begin. Okay, this is importance of initial value theorem. If you want the proof of this initial value theorem, the same way you can follow what we done for the final value theorem. Okay, now we will discuss about the transform of integral. This is what accumulation effect. This is also called accumulation effect. Okay, so this is a limit if if Laplace of f of t equal to f of s, then Laplace of integration of 0 to t f of t dt equal to f of s by x. So integral means accumulation. Okay, something is continuously adding up. So in Laplace domain, accumulation becomes divided by s. Okay, in example, if you just go through it, liquid L volume accumulating in a tank. And one more example, if you go and take energy stored in a system. So that means integral means divided by s. So divided by s means this is the slower response. Slower response. Okay, now we discuss about one more theorem, translation of a function. This is called time delay. This is called time delay or dead time. Okay, so if Laplace of f of t equal to f of s, then Laplace of t minus t naught equal to e power minus s t naught into f of s. Okay, so now here see, here the original function start with a time 0, but the delayed function start at time t0. So this delay appears an exponential term in a Laplace domain. Okay, so if you want to know some example, transport delay in pipelines, that time in a chemical reactors. Okay, so time delay in a real time becomes exponential in Laplace domain. That's what you should know about. So this delay does not change the shape, it only shifts for the response to the right. Okay, so this is what translation function. Now what we discussed till now, the initial value theorem tells how system start, and final value theorem where the system ends, and integral term accumulation, and then translation of delay, translation tells about the delay. So these four properties help us to analyze real process very quickly. So using these properties we can understand the system behavior without solving the complete equations or maybe the full equations. So next we will apply these ideas into derive a transfer function and system response. Okay, so all right, let us conclude today's complete lecture. So in this class I think we started with the process. So in this class we started with the complete video, PDC, process dynamics and control, where we clearly understand what is the process and why dynamics are very very important in a chemical and process industries. So then we introduced Laplace Transform, which is very powerful mathematical tool in process control, and we learned why Laplace Transform is required to convert time domain equation into simple algebraic equations, okay, in S domain. So after that we discussed the property of Laplace Transform, followed by Laplace transform of simple function. Like one is a step function, ramp function, exponential function, sine and cosine functions. We also understood the Laplace transform of a derivative, which is extremely important in modeling dynamic systems. So then we solved numerical examples. I applied inverse Laplace, and finally learn some important theorems and properties such as initial value theorem. Today that's what just now discussed. Initial value theorem, then final value theorem, then Laplace transform of integral, then translation of a function. So all these concepts are foundation stones for understanding the transfer functions, block diagram and control system analysis, so which we study in the upcoming classes. So from all these points now I can conclude. I strongly recommend that you revise these notes once and try to understand the physical meaning, not just all these formulas. Okay, so yeah, thank you so much for watching this lecture patiently. So we will continue this course in the next class, where we will move forward with more interesting concept in process dynamics and control. So until then, take care, keep learning. See you in the next lecture. Thank you.